I'm Yuichi Otsuka of IC Nagoya University in Japan. I'm talking about scintillation drift velocity observed by closely spaced GPS receivers in Indonesia. Target of this study is equatorial plasma bubble, which is a localized plasma density depression generated in the equatorial ionosphere. In the plasma bubbles, plasma density irregularities exist. Therefore, when the radio wave passes through the plasma bubbles, intensity of the radio wave fluctuates. This phenomenon is called scintillation. In this study, by using GPS receivers, we measure scintillation as a proxy of plasma bubble. In this talk, we focus on equinoctial asymmetry of plasma bubble occurrence and related phenomena. This is a previous study regarding the equinoctial asymmetry of plasma bubble occurrence and zonal drift velocity. This work has been done by analyzing the data taken at Koto Taban, Indonesia, during 2 years in 2003 and 2004. This figure shows local time and seasonal variations of scintillation index S4. We can find that scintillation occurrence rate is high in equinox with equinoctial asymmetry. The scintillation occurrence rate is higher in March equinox than September equinox. Right-hand side panel shows local time variation of averaged zonal drift velocity obtained from the GPS observation at Koto Taban in 2 years. It is found that the zonal drift velocity at post-sunset is higher in March equinox than September equinox. This paper suggests that high scintillation occurrence in March equinox may be related to the large drift velocity in March equinox compared to September equinox through the mechanism causing the eastward electric field at sunset terminator, so-called pre-reversal enhancement. Purpose of this study is to investigate equinoctial asymmetry of zonal drift velocity obtained from the GPS measurement at Koto Taban, Indonesia, during 2003 to 2016, and vertical drift velocity and FOF2 obtained from ion zone days near magnetic equator, Chunpon, Bakuryu, and Cebu during 2004 to 2006 and 2010 to 2015. We also study their solar activity dependence. Based on these observations, we discuss the mechanism causing the equinoctial asymmetry of plasma bubble occurrence. I will show the results. This figure shows scintillation index S4 measured by the GPS receivers at Koto Taban as a function of local time and season for each year from 2003 to 2016. Scintillation frequently occurs during high solar activity and doesn't occur during solar minima. We can find that the scintillation occurs after sunset and continues until midnight in equinox with asymmetry between March equinox and September equinox. The scintillation occurrence rate is higher in March equinox than September equinox. This feature is consistent with the previous study. Next figure shows local time variation of zonal drift velocity obtained from the GPS measurement at Koto Taban for 14 years. Two curves correspond to the zonal drift velocity in March equinox and September equinox. The drift velocity is shown as a function of f10.7. In this analysis, we have selected the data during magnetically quiet condition. The number of days when the data were taken is shown. Mean f10.7 for the two equinoxes are almost the same, so that we can discuss the difference of the drift velocity between March and September equinoxes without effect solar activity. We can find that the drift velocity is higher in March equinox than September equinox. This feature is also consistent with the previous study. Next, we show solar activity dependence of the eastward drift velocity in March and September equinoxes, respectively. We can find that drift velocity in March equinox largely depends on solar activity, although the drift velocity in September equinox doesn't show clear dependence. Furthermore, we have investigated the solar activity dependence of vertical drift velocity obtained from the iron zone near magnetic equator. Solar activity dependence of upward drift velocity is more clearly seen in March equinox than September equinox. In order to investigate mechanism causing equinoctial asymmetry of electric fields, we have investigated the solar activity dependence of FOF2. We found that FOF2 increases with increasing solar activity more clearly in March equinox than September equinox. Also, we found that during high solar activity condition, FOF2 is larger in March equinox than September equinox. From these observational results, we have found that when the plasma density is in the ionosphere is large, the zonal and vertical electric fields are large. As a result, plasma bubbles likely occur. Here, we consider the mechanism causing the large zonal electric field when the plasma density is high. During nighttime, electric current in the ionosphere is driven by the neutral wind. Because the E region disappears during nighttime, the current cannot flow so that the electric field is equal to minus U cross B. If the E region conductivity cannot be neglected, the electric current flows in the E region, so that the generated electric field is weakened. Relative magnitude of the conductivity between the E and F region controls the magnitude of the electric field. Large F region conductivity could contribute to generation in large electric field. This is a summary of equinoctial asymmetry. Plasma bubble occurrence, eastward drift velocity corresponding to downward electric field, upward drift velocity corresponding to zonal electric field, and plasma density during high solar activity are higher in March equinox than September equinox. Solar activity dependence of these parameters is more clearly seen in March equinox than September equinox. As a conclusion, we can speculate that in March equinox, due to high electron density, intense electric field is generated through the F region dynamo, so that plasma bubble likely occurs.